don't have to know what they're doing because that's what's the power. It's not rocket science. You just go, oh, you've got you said that you were redirecting this into, I know this has got to go at this address.
Their file is just for assembly.
It's the same instruction. The thing about that is it's good to know that instruction is compiled into your If you say, so if you use the word injected for the header, it does that way in return because that was so you say that it's harder because it's automatic, but at some point it's always these facts and facts and the net does that. Besides going back to where we were, that's everything back to where it was. So seldom used and it's almost always the best way of doing it. There are one or two places where it's actually possible to do it, but they are very, very few. The problem with this is if you say to people, you shouldn't really use it, but sometimes you have to, you go, oh, I've got to use it, style. There's nothing in this culture there's nothing in that system.
weekend cometh. Come on, quieten up. Enough now. Quiet 3 times. Obviously there's more people in now than there was this morning. Welcome, Sleepyhead. That's good. So the marks are up there. We had a good old argument. We finished. We put the room back together again for those lovely first years on Monday when we all finished and put places away. We had lots of argument, lots of discussion. Some of the posters were really very good. Some of the markers were a bit carried away and were generous, so we had to go back and knock a few off. There were a couple of, how should one put it, less well-performing posters than you would have hoped for. Some of the marks, some of the posters were terrible. Not really, no. Some of the posters were a bit below par on what I expected, but then the Q&A session saved the bacon, because we marked it so it was 65% presentation, 35% on Q&A. So if you did an average poster, you then had the opportunity to shine in the questions. Some groups didn't shine in the questions. Not looking at anybody in particular, but one particular group I interviewed knows who I'm talking about. Other group didn't know anything. One group in particular didn't seem to know anything and didn't seem to do anything. And we won't say anything about that group 15, will we? So, don't know what you were thinking with that poster, but it was very minimalist. And a minimalist amount of effort showed in a minimalist mark. So there you go. So hopefully you're happy with the marks. All 3 elements are marked. Group 10 was a first class performance, considering they answered the questions well, and there were only 4 of them, so good, well done to them. Other than that, I'm competing with you. You can talk, but I'll give you a chance to chat in a minute while I put the next slides up. So just give you an idea, the average of all those marks, by the way, was exactly 75. Remember I said I targeted 70 plus or minus 5. Understand Dr. Garforth always targets the top end of any area that he gets. Okay, so when I say 60 plus or minus 5 for the exam, I expect it to be 65. I don't expect it to be 55. I expect it to be 65. So you've now I got 75% on average on that part of the coursework. Most of you averaged, I think, better than that because the second exercise you really did well on because it was on paper and I gave you extra credit because you're doing it yourself. And it's very difficult to draw it, whereas here you've got computer packages, so we're a little bit tougher, but not that much tougher. I wanted to give one of the posters 90, and I can't remember which one it was now, but it's certainly one of the high-scoring 80s. And so it's either 12 or 13 or 20, partly because I've spent a hell of a lot of my life working on ZSM5, so I was quite obviously disposed to that one. But my younger PhD counterpoints pointed out that I'd missed some errors or factual inaccuracies and so on, so I said, okay, fine, I'll go with your mark. Pretty much so you know, you had 2 markers. On top of the 2 markers you had 4 moderators go around as well. So we were all dropping in and people were interested. So you will have had other people chat to you other than just me, as well as the 2 demonstrators. And actually, I had an argument with one of my demonstrators who co-marked with me, and I bowed to his judgment, because he gave a higher mark, basically. So I wasn't going to argue. And I said, yes, madam.
Sorry, is group final mark for all of it, or just for the poster?
Just for the posters. So what I'm saying, last average I think was about 77.5-ish for the second part. For the first part it was about 62.5, I think. I can't remember, 65 maybe. So you've gone up. Now, I said I was going to count the 2 highest scoring, so I'm going to give 10% of the mark to the first part, because that's your formative bit of learning falling over. And some of you did really well on that as well, so it's unfair to penalise you by not giving you anything. So 10% on that, and then I'll probably split the second and the third part either equally, or I'll go with the one that's a slight. Well, if I say that, somebody's going to be always upset because one will get a lower mark in one and a higher mark in the other. So I would initially make it nice and easy and just go 45, 45. So I'll go 10, 45, 45. But I'll have a look to see what the overall average works out and see if I'm being fair. You've had 3 weeks to do that. One group, in fact, got a low mark and didn't look like they put any effort in. But it wasn't just group 15 that I'm complaining about. There were other groups as well. So I don't know. I hope you enjoyed the exercise. We certainly had a tough time with your posters because now you've got the professional packages to make them look pretty, but we've also got the professional packages who try to look pretty in front of them who didn't necessarily know their stuff. But most of you did, and most of you got something out of it. So I hope it was okay. It's done and dusted, so there's no more coursework. For the MSCs, there's courses to test. There was a slight technical hitch with the test this week. It should have been this Saturday and Sunday, but it wasn't. And because I'm slightly slower in the lectures, I decided to give you all an extra week. So those of you who are MSc students now, you are doing the test for Sunday of next weekend, which I think is the 23rd of November, unless I'm looking at my marbles. Okay? So you have an extra week. To be honest, that's exactly on the pace of the course, so I'm not bothered. For the in-house class, that's fine. For the distance learners, they don't know any different, but they haven't had the benefit of seeing my voiceless slides appear on their computers somewhere. Okay? So, don't know whether you enjoyed it or not, but I can safely say that the people who attended the thing and gave you presentations, you did a very nice job as a whole. You were pretty confident, all of you. And 1 or 2 saves were made by guys who sort of didn't say anything, which was really nice. And I'm sorry I couldn't get to speak to more than about a dozen of you, so I apologise about that.
The podcast going to get fixed from now on? The last thing so wasn't working, but the rest of it.
That's amazing because according to what we asked, when I asked week 1 and week 2 and week 3 worked fine when I asked the class.
Yeah, they did, but the one last week didn't.
Alright, okay, sorry, I misunderstood what you said.
Yeah.
What do you want me to do about it?
I'm just asking why they're going to fail.
I'm going to try, but I mean I can't do anything.
Okay.
All I can do is I'll ask IT. Now I can tell you now that the industrialists are getting none of them because for some reason it's not working off site. So they're battering the IT department with questions. So I suggest you email the IT hotline or helpline and try, because bottom line is you don't need me talking to you over the slides. You think it helps, but you don't. You just read the notes and do the exercises. You'll be really fine. So for today's tutorial, I just want to show you this because I know you'll all come to the tutorial of your own volition on a Friday afternoon walking to James February. Question 1, exam question. Question 2, exam question. Question 3, exam question. Question 4, exam question. Question 5, exam question. Question 6, exam questions. And I've got the answers in front of me. They're all exam questions in tutorial 4. Okay? So, I'd attend if I was you. And yes, I will put the answers up, but I won't put them up that part of the course. So to be honest with you, the voiceovers matter, but doing the coursework, really, it's doing the tutorials that passes the exam for you, okay? And I know I put the exam and the answers up on Blackboard, but working them through with me and the demonstrators when I'm there is really great. The voiceovers, who's really care is for the industrialists who get let down, really. You guys are here. If you miss a lecture, I understand what you mean. It's nice to listen to the voiceover. But as this morning's class will testify, I can confuse just as easy as I can inform, okay? Okay. So, all right, everybody, let's get cracking. We've got to finish off with the lecture, and then we've got an introduction to the next part. So we're on end of chapter 4. End of chapter 4, and away we go. All I will say is congratulations, you beat last year's average mark for all parts of the coursework, just so you know. Okay, well done to you lot. Yeah, that's good. That is good, because last year they were good last year, but you were better. Maybe because some of you did the bio thing, I don't know. Maybe because the poster thing was relatively new for the bio and you had the opportunity and it helped a little bit, I don't know, but you were better. The average on the part 2 and the part 3 was 5% better than last year. 5%. In fact, I was hoping to take some marks off you, but now I've actually given you extra marks, so good are you. Now then, I thought I opened these things up, but obviously I didn't. Forgive me, just a little bit of fluffing around, apologies. Right. So we talked about, and I'm flicking that up, and maybe we're on voice. Yes, we are. I'm flicking that up to remind you what the ideal pore model was supposed to look like. It was a tube with a blocked end. An inkwell pore is what we refer to them in the trade. That's your model. What we did in class was we introduced the effectiveness, just so we know where we are. Effectiveness. And then finally, we said, hey, hold on a minute, but actually pores aren't straight inkwells, they're actually ziggy-zaggy lines, and the effective diffusivity is actually different. And that's where we stopped. Now in the notes, there's a little addition to what I seem to be not have bothered putting such a trivial thing on the slide. So the next slide goes on to explain what slab geometry is, which is that one. So I'm going to put that one up, but what I'm going to do is allow you a minute to focus, because I know it's Friday afternoon. I want you to read the next bit of words that are underneath the ziggy-zaggy pore. So where we're talking about the ziggy-zaggy pore picture, just read the words underneath that, just to introduce what we're about to just quickly do 10 minutes on. So if we've now got, ignoring the fact that tortuous shape and variable shape, the length dimension can be taken as equals A0. So we're splitting the pore from the middle, and the pore in the middle now is minus A that way and plus A that way. And then we take into account the surface area over the volume, and we've got an equation. That's the bit I want you to look at. I want you to take that in, and I'll have it. So, focus. Bulk concentration. So now, if you look at the slide above you, or you're looking at the slides, you're just being clever and being ahead of the game. Concentration in the bulk. This is the imaginary boundary layer. And then we're into the concentration at the start of the pore. So imagine that is not related to that line there. Good question. Okay, so we've all got this idea of this simple formula. The reason I've drawn your attention to that simple formula is you might find it useful in an exam question, but you'll certainly find it useful in the tutorial question today. Okay? I'm just drawing your attention to that. What do I need out of that bit? Not a lot, other than the understanding that you can end up with a calculation that allows you, if I said in an exam question, well, calculate the pore radius given some conditions with no information whatsoever, and then you would just write down the volume of the pore over the surface area of the pore, and you would end up getting an equation. That equation is equal to 2 times the pellet porosity divided by the bulk density over the surface area. That's basically what I want you to do. And that would be an exam question. And there's a context in the tutorial problem, which is in my top pocket, which is tutorial 4. So let's just take one geometry at random. Now then, there's lots of stuff in the textbooks, and I do recommend Fogler, chapter 10 in the 4th edition. Okay, that's the 4th edition. It might be chapter 11 or something in the 5th edition, but the 4th edition is chapter 10. Yes, everybody goes, brilliant, he's told us what to read. It's only one chapter for the whole course. Unfortunately, it's 114 pages. So it's not such an easy treat as you think. But it is a really good read. By that, I mean it contextualizes all these courses, and I've picked out favourite bits and added a bit on Real Catalyst towards the end of the course. So it's really worth reading chapter 10 of Fogling. You can download legal or not so legal copies all over the place. So please feel free to do that. And if you're stuck on going to the library for it, there's about 30 or 50 copies in the library as well. A bit tatty, but they're there as well. What else do I have to say? So let's now focus on a slab geometry. That is a slab geometry. So the key thing is to look at, well, what are the terms in the equation? Well, first we've got the mass transfer. So the gentleman on the front row yet again asked the question. So look at the line. That dotted line on the end is not meant to line up with the cylinder. It's meant to be the boundary layer. So we've got a line, then we cross it to get to the catalyst, which is now a slab. The slab, therefore, has dimensions which are both lengthwise and across and lengthwise. So we've got that in the equation. So if you have a look first then, we've got the concentration in the bulk, which is the total concentration. Maximum rate, concentration at the active site is equal to the concentration in the bulk. That's the maximum rate. But first we've got the rate of external mass transfer, so we've got to get across. Then we've got to enter into the structure to get to the rate of reaction at the active site. So you've got two equations. External mass transfer rate, which is the area that we're going across. So A dash is actually the area that it's moving across. And you can imagine that as the slab, because we're trying to push it into that slab. So it's the opening. And then it's times concentration in the bulk minus concentration at the end. The rate of reaction, remember, should be the surface reaction rate, because we're assuming it's all surface reaction. Keep saying that, 75% are all surface reactions. So the surface reaction rate times the concentration that the active site sees. So not the concentration in the bulk, but the concentration at the active site inside the pore, not necessarily at the door of the pore mouth, but in the pore. So the active site concentration is Ca0. Ca0 is related to Cab. We hope that you guys have done the best you can to set it up right. So we hope that the mass transfer is as fast as it can be. Two equations set equal to one another because we should be at steady state when we're operating the reactor. Therefore, we can manipulate the equations to get concentration of A0, which is at the surface that's doing the reaction. Now, of course, we don't want that because we're engineers. We want to know something we know. We want to know the concentration in the bulk. So you can rearrange that equation, and you should end up with the equation that you see at the bottom. So if we look now, the average volumetric rate at the surface of the reaction will equal the surface rate times the bulk density, times the surface area that it's available to it, times the effectiveness, times the concentration that is seen. Yes, sir, the question, I didn't see that, sorry.
What's the small a?
A is going to be the cross-sectional area. I should have said that properly, I didn't. But thank you for giving me the time to correct. Okay, so the little a is just the distance, but the big A is the cross-sectional area. So the little a is just the distance. Do you remember? I'll take it back one. Oop, sorry, going the wrong way, giving you all the seasickness, sorry. So, I don't know why that convention exists, but that convention exists. I don't like it like you don't like it. I like x plus x minus x, but that's not what they do. They do plus a and minus a, okay? That's engineers for you. Don't ask me why they do that. Yes, sir. You've moved. No, you haven't. You've moved from there. Remember.
So you asked, you said in the morning that you don't have a powder catalyst because you have a big pressure drop, a large pressure drop, right?
Oh, okay. Yeah, go on.
I mean, didn't we discuss in the first lecture,
Come on, guys.
that we have like some catalysts that are spread out evenly in the liquid, and I got an idea that they were actually a powder.
Oh, okay. So what you okay? Now, Hedrick, so how would you? So the question is, I think, and you can clarify your question in a minute. Okay. So I think what you're asking me is, we talked about a perfect catalyst, and we talked about the dispersion or particles in a bed. Heterogeneous catalysis, by definition, is two-phase. It's usually gas-solid. Okay. Liquid solid is slower, more complex, but generally just a pain in the neck. Okay? So liquid catalysis would probably be done homogeneously anyway if it was organometallic stuff that's in drugs and various things. If the other type of organic of liquid catalysis is the one that we don't want to know about, which is also unhomogeneous, but is usually done in sewage farms. You've got bugs doing the job for you, and it's extremely slow rotation and extremely slow processing time and large volumes. Heterogeneous catalysis, you've got a particle and you've got a bed, and the bed particle size cannot shrink. Now then, ask your question again, because you put down the groundwork, but you didn't explain yourself particularly well.
So my question is, can we have a catalyst which is a powder?
Yes, but that would be more like a slurry reactor. So it would probably be a liquid phase reactor. If you had a powder, define powder I take to mean very small particles. How small are your particles in your powder? Let's say they are not millimeters long, they are half a millimeter long, maybe a quarter of a millimeter. I use pellets in a little batch reactor that are a quarter of a millimeter. You wouldn't use those in your reactors, because you'd never get the amount of material through without blowing them all out the end, because you'd have too big a pressure drop. So on a big scale reactor, your scale, engineered scale reactor, my scale is a pen reactor. Pick a pen up, put your finger over it, that's the size of my pen in a reactor. Very small.
And what limits the
So your
surface
particle
area?
size would need to be big. So what limits your...
Your surface area per unit mass per gram of a catalyst that would take.
Good exam question. Make them up this year, that one. I'll let you figure that one out. Think about it. Here's your piece of wood. I'm drilling your holes in it to make your pores. Only so many holes before the thing falls apart. That might be an answer, and there might be a number that you could put on that, and that would possibly be an exam question. So save your breath. Okay, so back on track. Sorry about that, class. Right. So remember, we're having a discussion from this morning's work, which is all about T modulus, and here we're going to just calculate some basic equations around it. So the squiggly E is effectiveness, for those that have missed it. The A relates to the length scale along the pore. The pore here is no longer this long inkwell that we talked about. It's now a slab, which is a cylinder with a hole in the middle. But it's expected that all the surfaces around it are non-porous, so the pore is just the hole down the middle. So it's just a length by an and a cross-section area to give you the total volume. So that's what we're talking about, just so I make myself plain. That is pretty common in many of the textbooks, so you should just be able to pick up the textbook and understand what that means. If you're having trouble with it, worry not. I'll try and make it even more simpler. So look at that top equation, which is the average rate. Remember CRE1, which is kinetic. Your rate on the first order equation is R equals KCA. That's exactly what that says, except we've now added in this mythical powdery stuff that is probably a pellet, or a wormy-like thing, or something like a cylinder. So that then adds in additional terms. Now what we've done is we've got from the previous bit, which you've got in whole in your handbook, you've got the CA0. So if we substitute in for CA0, we end up with it in terms of what we want, the concentration in the bulk. So we measure what we put in, we measure what comes out, we've got our terms in our engineering way, and you're able to then manipulate the equations, and you end up with this additive surface reaction and mass transport, and that should look familiar. And the reason it should look familiar is because you did it in the first week. It's right in the very first lecture in the introductory concepts, or the second lecture in introductory concepts, which says, what resistances do we have? We have the surface reaction, we have the diffusivity, and we have the attempt to get material across the boundary layer. Now, if you're still puzzled, because many people ask me, Dr. Galforth, Arthur, Dr. G, whatever, what's in the back of the handbook? And what use is that to me? Well, in the back of the handbook is a little bit that explains that bit. Except it's in a classical textbook that's used by just about everybody who's anybody in industry. And it's by a chap called J. Richardson. And I photocopied the bit that explains that, and it's at the back of your handbook. So do take the trouble to look it up, because I can just say, this is this, you add this to this, and you get that. And isn't it great, because now we've got an equation which allows us to get information here. But actually the purpose of it is also written down in longer sentences, more detailed explanation, and is a classical text for you for the rest of your life if you're in reactor design. Okay? So it's in the back of this. The reason I say that is I've picked out 4 textbooks and I've picked out the relevant bits and put it in the handbook for you. So you don't have to do anything other than look at Wikipedia, have a route around in Fogler, because I haven't copied that, and read the handbook. That is why the external people tend to get 5% better than you. They've only got 1 course to study, now they've got 2 with Tom, so that'll slow them down a bit. So they've got 2 courses to do in industry, whereas you are in university doing 6 courses. So it's a bit easier for them than it is for you. But it's twice as difficult this year, I would say. So what you've got now is you've got the overall effectiveness factor based on concentration in the bulk. And you can see the equation is there, and previously what you had is that. You can see that the overall finished equation looks like that. We've got some idea of length scale, but we've got bulk density, surface area, effectiveness in this term, which is the reaction term, and we've got the mass transfer constant here in the equation. If we had a diffusivity effect, where is the diffusivity effect? Well, it's going to be somewhere in this one, isn't it? Because that's where the effectiveness comes in. So we've got mass transport, diffusion, and reaction rate. Why am I stating that slowly? For the simple reason there are 3 parts to this course. The 4th part brings in energetics, and we'll talk about that, about reactions. And that's the bit how I determine whether you guys are operating in the wrong regime or I'm operating in the wrong regime, and we've got issues. And we've got that to come in a couple of, well, probably next week, actually. So what's the important thing? The diffusivity is in there. What is the effectiveness? Normally, what are we targeting? So we're targeting it as a number. What do we want it to be? Do we want it to be 0? We want ml to be 0.5, not effectiveness. Effectiveness we need to be 1, but it never quite is. So ml, which is the Thiele modulus, equals 0.5. That's the key thing. So if that becomes 1, we know this is fixed, we know that is fixed. That just informs how much you actually put in your reactor. This then is also a constant, so actually that term just looks like, oh, okay, so once I've got, I know how much voidage I've got, I know what my skeletal density is, so I know how many holes are in the catalyst, and then I'm able to calculate how much I need. So now it's real simple. You're just doing first order kinetics on A goes to B, and its rate is equal to KCA again, because these things are fixed. But as long as this is 1, if this is what? If this is now not working, what is it? So it's not quite 0, but it's got an ml of 10, thank you. So if it's got an ml of 10, then it's effectively a very poor catalyst, and we might get only 20% into the poor, and the rest of the catalyst is a waste of time. If that is now ml is 10, that is equivalently proportional to 1 over ml, right? So therefore, if we change the length of the catalyst particle, we have effectively made the catalyst better. Because we've made the path length, that length of corridor, which I have to get up and down. Let's say I have to run up and down that once. I can do that, and I might go when I get down here again. But if I had to do that 20,000 times, I'd be dead after about the first 10, probably. And that would be the end of the class, and you'd be delighted. The exam is written, you don't need me anymore, so that's fine. You've got Fridays off without Tom. So we want to cut it down, so I only have to do that. So now I'm doing step aerobics. I reckon I could do that for about 20 minutes now without actually having to take a line and take a breath. But that's okay. But that's all I'm talking about. You engineers, blunt instruments. This is 1, you assume, or near to it, fine. We don't have any diffusion effects. Do we have any mass transfer effects? You should have sorted out your reactor so you know the boundary layer as thin as possible without blowing the damn stuff out at the end of the reactor. So you should be able to eliminate that. Then you're just simply down to how much do I need? So when you're doing your design, or when you're looking at the bits of kinetic information, that kinetic information is just informing you on how much catalyst you need. That's it. If the kinetics are very complex, and usually they're more complex than first order, usually they're multiple reactions, then you try to break it down because you're engineers and you break it down into individual steps. Let's assume I've got 5 little bits of a reactor. My mechanism is this, 1, 2, 3, 4, 5. And then you try to identify which of that reaction mechanism is the slowest bit. Then you'll say, okay, that's my worst bit. Now I'm going to size my reactor on the slowest bit. I'm going to forget my other stages, just pick the slowest bit. And in the end, whatever number you come up with, you times it by 1.5 because you're good engineers. It's as simple as that. If you look at me like that's some kind of revelation. But you do. Add 50% design failure capability, bingo. We'll show you what happens in the next lecture. I was hoping to get to it today. I'll show you what happens in the next lecture when you don't actually make the hole on the reactor big enough. If you don't make the hole to get out of the reactor big enough, you kill people, and hopefully it's not yourself. Okay, so I'll show you that next time, and it will be linked to parametric sensitivity. You've done parametric sensitivity in second year, so it wouldn't hurt you to go back to CRE2 and have a look at temperature sensitivity around reactions, but we'll do that next time. So, just by summary, and hopefully it means something, in this way, the combination of the pellet effectiveness, the external mass transfer can be expressed in overall effectiveness factor. So here's our two equations we just derived, very simple arithmetic equations, nothing to it, and we've got an overall effectiveness term over here. So what are we doing? We're taking this that we probably can't measure, or we can only get a handle on, and we're swapping it into that. So we're just literally making this fixed fudge factor. It's a fiddle factor to allow us to better ascribe kinetics and modeling to our reactor system. Fingers crossed. But hopefully, certainly you remembered what I wanted you to remember. I've got the message of ML 0.5 and ML of 10 in there. I've got the message about what a pore looks like, so you can define the model. You can set the model up. So you can show me in a diagram what the model is. You can show me the inkwell, you can show me the zone moving through. You could actually derive some of the equations. The concentration profile of the first order is what we've done. The effectiveness factor and the Thiele modulus plot against one another, remember, looks like that. It's basically, for the bit that we're really interested in, predominantly a straight line where the gradient is 1 over the Thiele modulus, 1 over ml. Apart from the very top of it, where ml is now going towards 0.5 and the catalyst is very effective and we don't have the problem. So remember the axes, remember the curve, remember the curves which hopefully Tom left behind for me, which he did, bless his cotton socks, he's a lovely lad. So ml 0.5 and ml 10. So on this side of the class had the answer written when I was asking. It should have been a bit more speedier, but it's there. So remember that. What does it mean? It talks about the effectiveness of getting your concentration into, go the other way around, go up. So the effectiveness is getting the concentration down the pore length. So that's what effectiveness and Thiele modulus mean. Diffusivity means, tortuosity means, well actually the path length is no longer straight, it's doing that. Therefore it's up to twice as long, therefore we're going to divide it by half, etc., etc. We've looked at one example of an arbitrary shape. There are 3 real examples. One is a pellet, which is a cylinder, one is a plate, and one is a spherical ball. If you meet any other types of catalysts, the only one you're likely to meet is that steam reforming catalyst with the big chunky thing with a hole down the middle of it. And that is pretty much all the catalysts you'll ever meet. And that, endeth that. Now the next bit adds another complexity on there. And we need a little bit of revision. So what we're going to do, because it's Friday afternoon and I'm nice, just going to do a little bit of revision, which may or may not be in the handbook. So what do we want to know now? We've got to the point where we've understood the setup of the reactor. We've understood the basic components, but now we want to do some fixed bed reactor calculations. So we want to do the modeling bit. I've blanked out one of the sections because it's in the notes and you can study it yourself. I want to look at the one-dimensional model, I want to look at isothermal, I want to look at adiabatic. And you remember that isothermal is problematic because you have to hold temperature. Adiabatic is really quite nice in engineering terms because you just let it do what you want. Because it's very nice unless it runs away. And by that I mean it doesn't get legs and it runs away. I mean it blows up. And parametric sensitivity is the bit that tells you about it blowing up. Great exam question. Lousy answers year in, year out. So this year I've given you an example of an explosion and a video clip that we'll watch from somebody's home CCTV camera 5 miles away. It killed the engineer that designed the plant.
it killed 4 process operators, and it only happened 3 years ago. Okay? I mean, no, it isn't in safety. Okay, so you haven't seen it before. So let's just do a bit of revision, because the punchline, which is next Friday, so that's a nice little, book to catch you for next week. Okay, so plug flow reactor. Let's remember what it looked like in CRE2. So it's a straightforward curve. So we used to have the volumetric, the volume of the reactor over the flow rate at the start of the reaction, which is FA0, is a term, and we used to increase the conversion as you reduce the flow rate. Look at the data set. Remember what I said about data and star maps. Yes, you can draw a curve through that, but you could also draw 2 straight lines through that, one of which seems to be very fast and the other seems to be very slow. CRE3, integral reactor versus differential reactor. Differential reactor, very slow changes in concentration. Differential reactor, very low conversions. Last week we talked about Langmuir-Hinshelwood, and we talked about an initial method on how we might distinguish reaction kinetics. One of the ways to do it was very low activity, very low conversion. So we imagine our equations now without the product in them. So it's simplified all our Langmuir-Hinshelwood kinetics, our Hillel-Rideal kinetics and all that. So if you look at the bit that's the straight line bit, that bit could be considered to be very low conversion. So as we move to the origin of the plot, that side, to the left-hand side, we're going to very low conversion, or very early times on stream, but we're trying to push it to the lowest conversion. As you go up, of course, it starts to curve off. It asymptotes to basically a slight gradient. That is generally known as an integral reactor. So an integral reactor is at conversions that are greater than 10%. A differential reaction is generally considered to be conversions less than 10%. Better to be less than 5%, because the less confusion with the products being produced and any side reactions, the lower the conversion should be. That simplifies all the kinetics and allows you to get at the basic fundamental kinetics and deconvolute everything. So if you now look at what CRE2's equation was, so all of you that have been struggling to get hold of Aileen and Phil's handbook from last year who are MSc students, you should have got hold of one. The only bit that I really want you to remember is that equation. And the fact that if you take slopes of this curve, you will get at the rate. The problem is where you take the slope. Do you take it at the beginning when it's straight? Do you take it as it's turning off? Or do you take it at the bit like that? And now you've got 3 rates. You've got an initial, an average of the initial with the final, and away you go. So you've got a problem, especially if your data moves around a bit. So where your x's are not next to one another, and they're deliberately not next to one another, you've got a problem with the data that you get out of the lab or out of your real reactor. But that's all I wanted you to remember, that reaction rate is a function of the slopes. That's your basic design equation. Take the slope, which is a differential, remember, and you end up getting a function of you get at the rate of the reaction. So you can always get kinetics on anything that's in the literature. You can just do it yourself. You could plot that plot on anything that's in any of the literature that maybe they've never done. And you could say, okay, I'll have a look at that and see what kind of rate I get. And then you'll look at another paper and you'll compare the rate you got with the rate they got. And you go, oh God, it's out by 100. Okay, so now we have 2 reactor designs. One with 1 gram in it, or one with 1 kilo in it, and one with 100 kilos in it. And somewhere in between is going to be your design. That's how you approach design project when you don't know what you're doing. Simple steps, bit by bit, knocking down what are, in effect, Aunt Sally's. This is my reactor. No, it's not. It's too big. That's what I should be having. No, it's not. It's too big. That's what I should be having. And that's what I want you to be thinking about when you're doing design project, not now, for next semester. Okay, so does this make me any kind of expert? No. What it basically is just a reminder that here we've got an isothermal reactor. So we have a jacket. We've got a temperature of the jacket. This is all CRE2 basically. We've got an element which is moving between Z and Z plus dZ. We've got a flow rate which is a molar flow rate, and we've got a mass speed rate. We've got particles now in our tube which are the catalyst particles. We should really say catalyst pellets or spheres or shapes. Those spheres are then interacted by the feed. Obviously I've not filled the whole blessed thing. It's meant to symbolize the whole thing is full. Because we're talking about heat now, of course, we'll need to be talking about mean specific heat capacities. A thing that's an anathema to a chemist, because specific heat always changes. There is no such thing, but in engineering terms, it means you approximate between two numbers over the scale. Is that a stretch, young man? It's all right, that's fine. Just checking. Okay, so that's your basic setup, a cross-sectional aerial flow, and we end up with some equations. The reminder of the CRE2 is at the top, just to keep you focused. And then if you look at what we're doing at the bottom, we're doing a material balance on the incremental length. So if we're looking, well, I'll do the isothermal case in a minute. Let's set the whole thing up. So you've got the reaction rate. Remember now that our reaction rate, according to what we've been studying, has got this effectiveness factor in it. We've got the rate, which is dependent on the conversion and the temperature. That's obvious. It's determined with the conversion because of the reaction and the temperature because of Arrhenius. Is it exothermic or is it endothermic? So that's the energetics you're asking there. So that's a straightforward reminder. You've got the A times the length, so you've got the cross-sectional aerial times the length is equal to the flow that you put through it times the conversion that's observed. You rearrange, you end up with the following equation, which you know because it's just the same. Except now you've done it by length, and you've got the conversion over the length for that element, and that gives you that equation there. I just want to check that that actually is in the textbook. It is. And I just want to check whether all that explanation is in the textbook. The only bit that's extra is the reminder. Now, if you're to do a heat balance, you and I must know by now, because you've done enough of it, you're going to have UA delta T in there somewhere. You're going to have the flow rate, the mass flow rate times the CP, which is the heat capacity, and the change in temperature. And on the other side, you're going to have the flow rate and the conversion times delta H. That's your stuff from CRE2. Go back and have a look at it. It's the first introductory lecture about Chapter 5, which is on heat integration in the reactors. The first 4 bits, which I think Aileen covers, is all about doing mass balances and about new reactor styles. The next bit, which Phil Martin covered, ends up being the heat integration bit. So if you want to go look back at CRE2, that's the bit that you need. The equation looks exactly the same as you've got there. Key bits that you always mess up when you're doing this sort of thing is you mess up the delta T's, and you've got the temperature, and the temperature J is the temperature of the jacket, remember, from the diagram I just showed you, and it should all be on the page in front of you. Oh, did I say everything? Not quite. So just the last bit of reminder, you've got the heat from the reaction on the left-hand side is equal to the heat removal and the heat gained. The heat gained could be a heat lost as well, and you end up removing the equations around depending on what happens with your CPs, which you get from the literature, of course. Whether it's exothermic or endothermic, that's what matters. Okay, so we're doing the heat balance across this little incremental bit. That's all I want you to do. And you end up with that equation, which is the change in temperature with the little increment that you're looking at is equal to the flow rate over the mass flow times delta H over the CP times the conversion over the length that you've looked at minus UA delta T over the mass flow and the CP in it. Now you can rearrange the equations yourself and have a play, and you can look at the notes as well, but there is no trick, there's no sleight of hand. It is straightforward algebraic manipulation. So for a tube, you would get that equation there, and you would change it because you've got the diameter, and it ends up being 4U d g c o times T delta, well, delta T, which is the temperature and the temperature of the jacket. So it's a cooling liquid minus the temperature of the jacket. So that's the overall equations, but that's not the bit that I really want you to focus on. The bits I want you to focus on are the 2 examples, isothermal and adiabatic. And I think I'll just do one, because then we can stop and we can wander over, if I haven't killed you, and do some exam questions with my lovely demonstrators before we get onto parametric sensitivity, and I show you a little video next week. So, isothermal's nice because the temperature doesn't change. So in other words, the temperature across this increment is no longer changing, therefore dt over dz equals 0. Therefore, you need only to solve the mass balance equation to figure out what's going on. Okay, so let's just think about that in terms of something you've just read. So you've now got a set of data, conversion data, versus temperature or time on stream. You've looked at it, the people have measured it, they've done it, they've given you the description, you automatically say, right, okay, they've tried to keep it isothermal, let's assume it is isothermal, they've got this rate. Big problem for you all. It's never isothermal, if it's endothermic, it's going to drop in temperature, if it's exothermic, it's going to gain temperature. They're going to spend their lives, so are you, trying to control that reaction to make it either not stop or not blow up. But one thing's for sure, most chemists, me, until I came into chemical engineering, would never put a thermocouple in the middle of a reactor to tell the temperature. Most engineers still don't put thermocouples inside their reactors because it's too expensive and they never think to do it. And that's why Hickson and Welsh blew up not long ago and other places blow up, because you don't put enough sensors in. You think you do. You think as new people, it's obvious they're bound to, but no they don't. Every time you put something in to measure something, you add complexity to a reactor system. Every time you add complexity, you add human error. You had cost and human error together, you have disaster. So they try to make them idiot-proof, but in the process of making them idiot-proof, the guy who's used it, or the girl that's used it for 30-odd years, just retired and somebody new came to look at it. You are now the idiot in front of a bomb. The problem is that's what happens to you guys, and hopefully it never happened to you guys, but that's what happens. So beware, the real world is a hell of a lot sophisticated than the tools you actually use in the university. So let's have a quick look at it, because maybe there's somebody to come in here in a minute and maybe there isn't. So need to solve for the mass balance, so that's the only equation you need to worry about. You've scrapped the other equation completely. No need to consider it. For a first order reaction, we've got effectiveness, reaction at the surface, bulk density, surface area, times 1 minus E, which is the tortuosity or the voidage. Let's see, we'll figure that one out in a minute, times the concentration. And that's the bit I just want you to have a look at. You've seen those equations. You've most definitely seen this equation in CRE2. Isothermal case, we've now rearranged it, so we're trying to get it in terms of conversion, because that's what we want to measure. We want to measure a conversion incrementally down a bed. Why? We've got x0, x equals 60%. That's what I will tell you in a publication, but I don't tell you how it changes down the bed. You want to model it, so you have to try and break it into a lot of CSTRs, lots of little reactors, so you can get an incremental change. Therefore, you want to work at the lowest conversion you can and break it into the simplest system that you can. Okay, so look at the equations. They are just rearrangements and they are summations. So if you look at dxa over dz, you end up with that equation. Eventually, if you talk about integrating it, log 1 minus x should spring out of you as a straight first order integration of the rate equation to give you log minus log e to the base e, 1 minus x. In other words, log 1 over 1 minus x should be there. And then you end up getting it in terms of conversion, which is 1 minus e to the k, which is the rate constant, times the incremental length. Now I happen to, there are people trying to get in, so we'll stop in a minute. I have done a model which I will work through and give you a free copy of, which will help you with design, which is an incremental integration down a bed, which does exactly this for a reaction. So I will give you that. It's part of the notes, but it's meaningless without the Excel spreadsheet. If you look at the Excel spreadsheet, you'll be able to work it out. And we may have time to play with that in one of our sessions next week. We might do it in the tutorial, in the slot before the tutorial, because it might be interesting. I'm going to stop there because that's the final equation that you can see. And why is it turned into that? You've taken that and you've substituted it in and it looks like that. But it still looks like CRE2. Okay, now then. So, because we're going down the road and it stopped raining, I'll see you down the road for the tutorial. Those of you making